Consider the set of all matrices in R in Mn of R, where Mn of R is the set of all n by n matrices over R with the trace equal to 0. Here consider the set S. Consider the set S of all matrices in Mn of R with the trace is equal to 0. Then which among the following conditions are true? First one is that S is nondense. Second one is that S is compact. And the third one is that S is connected. Okay. Here we are considering Mn of R as the space Rn square. Then the set S will be a subset of Rn square. Okay. Now S is the set of all matrices B in Mn of R such that trace of B equal to 0. Here this is the set S. Now when we say that the set S is nowhere dense. S is nowhere dense if the interior of S closure is empty. And when we say that S is compact if every cover of S has a finite subset. Equivalently, a subset in Rn square is compact if and only if S is closed and bounded. Now, when we say that S is connected, S is said to be connected if there does not exist two open sets U and V. If there does not exist two disjoint open sets, that is U intersection V equal to 5. So, if there does not exist two disjoint open sets U and V such that S is contained in U intersection V and S intersection U, S intersection V are non-empty. If there does not exist such open sets U and V, then we can say that S is connected. Okay. Now, consider a function f from Mn of R into R, which is defined by f of a matrix is equal to trace of B. We know that the trace of a matrix is a linear function. So here f will be a linear function. So f is a linear function and every linear function is continuous. So here f is continuous also. Now consider f inverse of singleton set is 0. Here f is continuous and singleton set is 0 is the subset in R, closed subset in R. So we know that if f is continuous, then the inverse image of every closed set is closed. So here this inverse image will be closed and it is equal to the set of all matrices B in Mn of R such that what? F of B equal to 0, which means trace of B equal to 0. And this set is that S. So here S is a closed set. Okay, hence S closure equal to S. Now we are going to prove that S is nowhere dense. S is nowhere dense. To prove this, we need to prove S closure interior, which means S interior is empty. If S interior is non-empty, then there exists an element B in S interior. So here trace of B equal to 0 since B is in S. Then here I am considering a sequence of matrices which is defined by B plus 1 by K into identity matrix, where K belongs to the set of natural numbers. Then f of B plus 1 by Ki is equal to trace of B plus 1 by Ki, and since trace is a linear function, we can write it as trace of B plus 1 by K into trace of I. Trace of B is 0 and trace of I is n. Then we get n by K, and which is a non-zero number. Okay. Then and look at the sequence B plus 1 by K into I. As K tends to infinity, this will converge to B. So, and here this is a sequence of matrices which converges to B. And f of B plus 1 by Ki is non-zero, which means this is a sequence of matrices which does not belongs to S and which converges to an element in S. And we know S is closed. So this will be a contradiction. So our assumption is wrong. Hence S interior is equal to 5. Okay. Once more look at this sequence. This is a sequence of matrices which is not in S and which converges to an element in this closed set S. This is a contradiction since S is closed. So our assumption is wrong, which implies S closure is equal to 5. Sorry, S interior is equal to 5, which means S is nowhere dense. Okay, next we are going to prove that S is connected. Okay, S is connected. To prove this, consider two elements A, B in S and lambda be an element in closed set 0. Here we are going to prove that we know every path connected set is a connected set. So if this set S is path connected, then it will be a connected set. Now we are going to prove that S is path connected. So to prove this, I am considering two matrices from S and an element lambda from the closed interval 0, 1. Then the trace of lambda A plus 1 minus lambda into B is equal to trace of is equal to lambda into trace of A plus 1 minus lambda into trace of B, and which is equal to A and B are two matrices in S. Therefore, trace of these matrices will be 0. Hence, it will be lambda into 0 plus 1 minus lambda into 0, and which is equal to 0, which implies lambda A plus 1 minus lambda into B belongs to S. So, for any two elements A, B in S and for any lambda in closed set 0, 1, we have this combination is in S. Therefore, S is path connected, which implies S is path connected. Hence, S is connected. Okay. So, the given set S is nowhere dense and connected. Next, we are going to check that is this set is compact or not. To check this, consider a matrix AN which is equal to its diagonal elements is in this form. First element is n and the second element is minus n and all the remainings are 0. Also, non-diagonal elements are also 0. I am considering such a matrix AN. Here, trace of AN is equal to n plus minus n, which is equal to 0. Therefore, AN is in S for all n in n. Okay. Now, here AN will be unbounded as n tends to infinity. Therefore, we can say that the sequence ANs are unbounded sequence in S. So, S is unbounded. Hence, we can conclude that S is not compact. If S is compact, then S is closed and bounded. Here S is unbounded. Therefore, S is not compact.